Okay, let's continue. And so basically, I'll show you again how to do the filter design using the Octave tools. But before that, let's take a quick look at what these exercises 4 and 5 are all about. So in the fourth exercise, basically you will be planning a finite impulse response filter. Well, it says system, but it's, well, in this case, they are all filters. So basically, first one is to compare amplitude responses of different window shapes, and there try to find a window then which matches more than 75 dB stop band attenuation. And basically just insert the figure here. The next one, so that's matching the window shape. So remember the FIR filter design, 3 parameters. One is the cutoff frequency, which actually just gives the sink form there. Another one is the window shape, which actually gives you this the stop band attenuation. And then a third one is the window width, which basically tells you the transition bandwidth. Okay, good. Let's see. Okay, I think this is doable. I need to work on these exercises sometime, but anyway, they are still okay exercises, I think. So, and the third one is then putting everything in together, having a sampling rate fixed, then there's a cutoff frequency, there's a given transition bandwidth, and then basically a stop band attenuation. So in this exercise, what you would start is from the cutoff frequency. That defines the sink. Then the transition bandwidth. So transition, no, not transition, that's the last one. But the next stop is basically the stop band attenuation. Let me move it up here so it's actually it's on the right place. So this is the order you would do the design. So sampling rate and cutoff frequency will define that what kind of sink function you have. Then you have the stop band attenuation. That's how you select your window shape. And finally, you go and tweak the width so you get the required the transition bandwidth. Okay. And then there's also that max 2 dB ripple on the passband. And minimum order number. Basically, this is more or less obsolete here since we don't have the more sophisticated optimizing tools here. On MATLAB signal processing toolbox, there is an FDA tool where you can actually also tweak the stop band ripple. So if you allow some ripple, then you don't need that many points on the filter. So the order number goes down if you allow some ripple. But, well, and then basically this is a minimum order number, meaning that actually when you reach your cutoff when you reach your transition bandwidth, you don't go further. You don't add extra points. Okay, and then verify your design. Okay, fourth one, transforming this bandpass low pass filter to bandpass filter with center frequency of 5.8 kilohertz. Well, this is just simple modulation and normalizing it to unity gain. You already yesterday exercise was about normalizing your unity gain, so you should know that already. And then next one is actually design a high pass filter with the following properties: sampling rate given, Cutoff frequency, transistor bandwidth, stop band attenuation. Again, this actually, I think this should be up here. So stop band attenuation and then transistor bandwidth. So this is a high pass filter, meaning you start from the low pass filter. Remember what I want about the that cutoff frequency compared to filter bandwidth. Then I have a voice sample. Wow. Excellent. Let's see. Do I have what is my playback device here? No. Okay, I think that's fine. Playback. Wow, I can barely hear that. That was a voice sample, and your job in this voice sample is basically do spectrum analysis. And the original voice sample has people discussing in, and there's also some artificial noise there added. So there's a discussion, but it's basically there's more noise that you cannot hear anything what they are discussing there. And basically then you do the spectrogram or spectrum and mark which part you think is noise, which part is signal. Now you should actually get use your intuition at which spectral range you think the speech is and which spectral range is the noise. But when you do the this spectrum analysis, it's quite obvious which part is which. Then you define filter requirements, meaning that you actually defining the box. So where do you put the cutoff frequency? How much stop band attenuation you will have? What do you think is enough for transistor bandwidth? And then just, well, pick some type for it, and yeah, type, meaning this type is basically more or less the well, I would just leave it like that. So remember that high pass, low pass, band stop filters available, and then, well, FIR is our exercise about there. And then you have these parameters. You have set up the parameters basically the similar way as in here. So that's your starting point for number 8, which is designing an FIR to filter to match the requirements. Then you verify your design that you actually got it. So you compare your design with the box, and then finally you filter and try to figure out what language are they talking. It might be a little bit, well, I'm not sure how good you are all recognizing different languages, but I selected one of the major languages in the world. And this is not Chinese. This is not Japanese, I can already tell. Those are also major languages, something else. But still, say, millions and millions of people are speaking it. Okay. So one of the major ones. Okay, then let's take a look at the 5th exercise. It is IIR filters. Basically, this is about the same, except it starts from the band stop notch filter. The only filter on IIR systems that you can actually design yourself by hand, just setting the 0 and pole on the corresponding locations. Then basically the plot zeros and poles would be just seeing that if you are even close to the right answer. Okay. And then we have the plot 25 first values of the impulse response, just for fun to analyze it. Then the, let's see, did I have the, wait a minute, why have impulse response? Where do I have the, okay, I have the amplitude response already here. Okay, good. And on the 4, this is same. Practically, this is the same question as we had for the FIR system. This time, this is for IIR. Design the same system as on the corresponding question on 4th exercise, but IIR methods, and verify. Compare the filters. What are the main differences between the FIR and IIR system? 6th is basically the high pass filter design. Okay. Let me move a little bit of these things around, so actually that it makes a little bit more sense. So IIR high pass filter using the methods what we have. Then we already have the 4.7 was the FIR filter coefficients for that purpose. Here you would do the same thing, but design an IIR filter. So, and of course, compare how the filters differ. So the previous FIR and this IIR. And let's see, I don't have the voice for noises, but this is actually a fun exercise. You would do 3-band equalizer, meaning audio equalizer. Okay, this requires a little bit of explanation, I think. Let me do it on the whiteboard. So, equalizer. That one. So basically, on audio player, you have usually on an equipment, audio equipment, you usually have 3-band equalizer for one. So basically, bands are for bass, middle, and high frequencies. And so basically, there are 3 filter banks. In general, actually, this is fixed, so you don't need to twiddle the this middle band, since it's enough that you can adjust the bass and high frequency components. This would be just volume up and down, in the sense that these are always relative to each other. So you can fix one of those. But anyways, the system works the same. You have the one signal source, then you have 3-band equalizer, so low pass, middle pass, high pass. Then you have adjustable gain, still linear system is a scaling with a constant, but you actually have a variable instead of a constant there. And then you have summing amplifier. So basically this exercise about designing of that filter bank. So we have 200 hertz and 2 kilohertz the cut-off points for those filters. So basically it's the same point for both. Yeah. So basically you do on the ninth point you were doing those uh, filter banks, and there you have used the previous filters to adjust the tone of voice sample. So you, of course, you turn up the bass and you can say boom, boom, boom. And then drop down a little bit of middle section, and then you put a little bit more of distant so it makes more annoying noise. All right. But anyways, for this one, find a voice sample. If you cannot find any voice sample, then basically just use a microphone to record some of your own singing. Have a karaoke night, with your friends, and but be aware of the copyrights. Copyright of the, if you download music, make sure you have permission to use it. Okay, that's important. If you perform yourself, then you have a copyright for it. Or if you are recording in a public place, for example, just noise from the streets, that's free. And there you have plenty of opportunities to actually record that kind of noise. All right. But anyways, so last one is basically to get your own voice sample and filter it with this 3-band equalizer. All right, good. And then let's get to work. All right, so again, I have my octave here already running. That's nice. Just a moment, I'll check something. Yes, display is correct. So, not there. So first one, we have the FIR filter design. And let me first just pick an arbitrary number for the window size. We have this sync. Or should I start? Okay, I will set up some things here. First, the sampling rate. I will put just 1000 hertz for sampling rate. Just for fun. Wait a minute. Am I in trouble now? Yes, well, let's make it 44.1 kilohertz sampling rate. So audio signals, if I want to, test a filter, then basically it will be easier this way. Sampling rate of 44.1 kilohertz, and there, let's define, for example, the cutoff frequency to 1000 hertz. So cut off at 1 kilohertz. Good. So what next? Next would be to do the sync. And to do any sync, we need to first define what size, what is the window length initially. We can fix it later, but we need to a window length on the beginning. So let's put, for example, n equals from -10 to 10. Remember what I said about the symmetricity. If you pick this index values symmetric to 0, then you would get linear phase response. Symmetric with 0 gives linear phase response. If you don't have linear phase response on FIR filter, then you maybe have mistook something. That's fundamentally the only reason to use FIR, to have the linear phase response. Okay, then next we will try just rectangular window and see if we have the cutoff frequency set correctly. And so we calculate the HH, which is the impulse response. Before that, let me do something here. Fn equals Fs divided by 2. So this is the so-called Nyquist frequency. Just sampling rate over 2. I'm not totally sure about this now, but anyways, so we have the scaling factor Fc over Fn times sinc of Nn times Fc divided by Fn. I just hope that I have the pi already on that sinc. We will see if there's if the cutoff frequency actually goes into wrong place, then I know to adjust. I remember there was actually a difference between the MATLAB and Octave sync at some point, or was it the MATLAB and the MathCAD? They have different sync, but we will see. We will see it soon. So let me then just calculate the frequency response of that system, which is defined by the impulse response. HH 1024 points and sampling rate. And I hope that this will actually gives me the correct answer. Maybe. Yeah. So 1 kilohertz is somewhere in here. And that is roughly the 3 dB point. What else we can see? Well, the stop band attenuation is not great. This has fundamentally the same problem as the running average filter. It has the box averaging. Actually, what this is, the box average convoluted with this sinc, which does give you the cutoff frequency. So it's not a great filter yet. The only thing compared to the this box average now is that we can control the cutoff frequency, and that's the only difference. However, let's see what does it look like. So stem NNHH. So the impulse response itself looks like this. Okay. So if we actually go and instead of the using the box, but a weighted box, a little bit, tilted box, it actually gives you the cutoff frequency. If I go and increase the number on NN, oops. Let's make this 100 times bigger. And calculate the HH again. Well, this one of figure 1. HH HH1 24 FS. There we go. So if I make this one 10 times wider, what happens actually, it squeezed the transition bandwidth, but we still have the the stop band attenuation is going down a bit, but not drastically. So it was 20 dB before. Now it's about 50 dB, and we wasted 10 times more calculations now. So this is not the correct way of fixing the stop band attenuation. But okay, now we can actually see a little bit clearer. Okay, that is 1 kilohertz point right there. So we have the cutoff frequency at 1 kilohertz. So definitely sync helps there. And let me do the other figure again. But now we have we have just wider sample of the sync. All right. Next is to see what happens with different windows. Now I need to check something here. Excellent. So for example, on the list there was a Hanning window. For historical reasons, the function that gives Hanning window, it's just Han, and then you give it a number of points, and it returns the symmetric if you don't put the optional argument there. Symmetric is good. Let's put here a window equals to Han length of our NN, and see what happens. Oh, by the way, now we have a really long filter. It's 100 points. So, okay, maybe I should go down a little bit. Oh, why not? We have a computer, it calculates. So that's the Hanning window. How to find the other windows? Actually, if you go to the documentation, I think you can find. How do you find it? Oh, search there. Window. Okay. Multiple plots window. Does it have the global search? Plot windows, graphic objects, signal processing. Okay, there. Signal processing. So we have there on signal processing toolbox. We have also the window somewhere. Nah. Too many windows here. Let's see if we have window generator. Excellent. So there is also a function that returns M-point window from function F. Okay, can be black. Okay. So yes, we can. There's actually window generator here, but how to use it? Maybe there is a better help somewhere. Okay, let's try doc window. Duh. Finding help on Octave is not that easy. But actually, let's try something else. So if I just say help and that hun, we started from hunting. So I would usually they are on actually on the does it have help on other windows? No, I think we have to go to the again Octave window. Mhm. Mhm. Function window. Reference signal Octave Forge. Okay, signal. Okay, no. Oh no. SourceForge project sites are currently under maintenance. That's not good. Yeah. Oh boy. Well, we just need to yes. I hate guessing. So help. Han was one. Hunting was that Han, but then hamming was hamming. I think. Let's hamming. Yeah, hamming window is hamming. Then help on Blackman. Yes, so at least those windows you can check. Blackman, hamming, Hanning. Okay, good. But I started with the Hanning. Good. So what do we have? What do I have? What do I have? Okay, I have the window. I have also the index. I have impulse response of the sink itself. Good. Um, Now we need to multiply this HH with the window. So I'll just put new parameter, a variable, equals WW dot times HH. This will give me an error. I am not even pressing. Well, I'll press. Let's see what happens. Wait a minute. This should give me an error. Okay. It gave me a huge matrix, 201 by 201. Why? Because someone from the beginning of MATLAB and signal processing toolbox decided to put the windows. For some reason it returns a column vector, while the system coefficients are always a row vector. Multiply row vector with column vector, you get either a scalar or a square matrix. So we need to transpose, for historical reasons, we need to transpose the window. Otherwise, this will give you funny answers. So transpose is the single prime there. This is important. There. Okay. And let's stem plot that one in a new figure. 3. So what we are doing now, we are actually, so this is our new new smoothed sink, while this one is actually the original, which was just this box truncation, and the lower one is this smooth the truncation. See the difference? So I smoothed the edges, meaning that we have less high spectral components, and compared to that we have more low spectral components. Let's then compare the ah, hmm. Frequency response. I'll put it that one on new window again. HHWW. Haha. So this is the original frequency response, and this is the with the smoother window. Okay, look at the vertical scale. While here we have maximum somewhere at minus 50 dB attenuation, we are hitting 150 dB here. So actually 50 dB is right there. So this one dropped down like that, just by using a smoother window. What else happened doesn't really show up in here, but anyways, we our transition bandwidth here. I probably should zoom this a little bit. Do I have a zooming? Zooming. Okay, I will zoom it by selecting the axis. Hundred minus 100. Okay, so axis actually sets the current axis where my where the cursor is. The axis which is selected basically it sets the axis limits x and y. With some luck, no, it went on the wrong. So this one was active. I hate when that happens. So in that sense, MATLAB would be a little bit better to work on this kind of. So I need to do some fancy things like first I get get see. So basically, I get the object get current figure GCF, and it has two children. Okay. Get current figure, and I will actually take the property. I know this is so funny. Or actually, I could. Yes. Okay. Now I have the CC has two figures, and I think the other one is the. Let's see which one is the GCA. Okay, current axis is actually that first one in here. So I just set the GCA to that one. That should work. Oh boy. How does it go? Go like that. Maybe. No, it doesn't work. I'll do it the other way around. I will just do a new plot of that one. Sorry about that. I blame the program. Okay, so if we have the, let's see, we calculated, we can always just the same way as earlier. We can actually take the frequency response and the, so basically this one just calculates the frequency response and returns that to me. Okay. Then I can do a new figure, for example, that figure 4, and I'll just plot F, 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 and then 20 times log 10 of absolute value of HH. So absolute value of HH would be amplitude spectrum. And then basically 20 times log 10 of that would be the power spectrum in dB. I hope. Haha. Why it's doing it like that? Ah. There's a feature. I deleted that graph and it still was there, the old graph. But anyways, now I have it on the right window. Okay, maybe I can do the same thing for also for the original. Okay, let's see. HH2 is, oops, HH2 is that one. So this is without, and then we have figure. That's without the smooth window. H2, okay, there. So without the smooth window and with the smooth window, they almost looks the same, but not quite. Now I can actually go and do the axis thing on both. Okay. Ha! Why it doesn't select this one? This is so. Ha! Okay, okay. I just needed to select the correct figure. All right. Okay, so those are the differences on. So on right hand side there's the original. Okay. And basically you can see that the cutoff frequency is just about that 1 kilohertz. But then the stop band attenuation is not that great. On the left hand side we have a better stop band attenuation, but look at the transient bandwidth. So the cutoff frequency is right about the 1 kilohertz, but the transition bandwidth is wider. Okay, so if we now want to adjust the transition bandwidth, if you want that to be even narrower system, so faster drop on that the cutoff, then you would need more points. On the other hand, if this is already too high, then you can take less points. For example, if I wanted the transition bandwidth to be 500 hertz, currently the transition bandwidth is okay. Does it give? Okay, so that's in hertz here. It's 1.338. kilohertz, it would be the stop and start frequency. So I have transition bandwidth is 338 hertz. It's that distance. If I wanted to adjust that to 1500 hertz, I need to do the following. Hmm. It's easy. You take first the length of the current impulse response, okay, divided by that current, the transition bandwidth, and no, the other way around, divided by the modded transition bandwidth and multiply it with the current transition bandwidth. Here, so you are scaling with the ratio of those desired and others. So let's see. Divide by desired bandwidth and multiply with current bandwidth. Okay, it's always that way. Okay, so instead of that, let's see, length. Instead of 201 points, we need only 135 points. Okay, need only 135 as the filter width. Okay. So how to do it? We have to calculate it over. So new indexes from minus 60, 68, or 67. It doesn't make much difference. To 60, to plus 67, new width. Let's see, length. That would be 100 and that's 135 points exactly. Okay, cool. And then we need to calculate the HH again, and also the window. And then we do the HHNWW, and that's our filter. And it looks like that. And let's see, axis. There. So we actually adjusted the this one to have wider the transition bandwidth, not to overdo it. Since this is a cheaper filter again, so it's a less cost. It has the previous had 201 multiplications there and additions, and this has only 135. So it's a big reduction on the calculating cost. Okay, good. Phew, that was a lot of work. Fortunately, the modulation would be high. Do we have the Meeting already starting or? Hmm. Yeah. Did he arrive already or? Okay. Would you start without me? Just I'm still working on here, so sorry about that. It takes a little bit longer than I thought. So would you please start without me? I will be joining you. Okay. Good. Okay. Good. All right. Um, so axis. So that's basically how you design the low pass filter. Now, fortunately, how to make the high pass filter is easy, or the how to make that how to make the band pass filter is easy. So low pass to band pass is actually modulation with FM. So let's pick a modulation frequency. We had 1 kilohertz wide the band width of the low pass filter. For example, 4,000 hertz would be just fine to make the point. So, hey, wait a minute. I will make it 5,000 just for fun. So we have this HHWW filter, and we just make it HHWW band pass filter by taking that, and multiplying with the cosine 2 times pi times n divided by sampling rate. Right. This is the modulation. So let's take another figure. So how does this actually look like? Doesn't seem to look like much more anything that we already saw. How come is that one? Oh, there's something funny here. No, it should be just fine. Well, we will see. We'll see how it shows up. New figure, and just frequency response, band pass. New figure. Ah, what happened here? Hmm? Modulation frequency, yes. What is wrong there? Something is missing here. Ah, yeah. Thank you. That was so. That was so obvious. Yeah. The FM frequency was missing here. Yeah, now it makes more sense. Good. There we are. So yeah, modulation. So now we have that low pass filter on the both sides of 5,000 hertz. So again, remember that this method actually gives the half band of the this band pass filter. The cutoff frequency of the original low pass filter is half band of the band pass filter. Okay, and it's unscaled now. But the scaling factor is quite obvious, actually. I think if you scale that by factor 2, it gives you exactly 0 dB at thermal end. It makes sense since when you are modulating, you're moving the center to two directions, positive and negative, the frequency axis. Okay. Then the high pass filter. That also was quite simple. HHWW high pass. From the low pass filter, we just multiply it with the -1 to power of n, well, or cosine pi n. That will give you the same. But there we go. High pass scaling factor away. There you go. Okay, so it just swaps the frequency. But remember now, okay, while we have the cutoff frequency here 1 kilohertz, now it's 21.1 kilohertz is the cutoff frequency. The bandwidth is at 1 kilohertz. Good. And then finally, the low, band stop equals to low pass plus high pass. Just remember to both that those both filters must have the same length. In order to do the addition. So high pass plus HHWW. There. But of course, this is, my high pass filter was just transformed from the low pass just like that. So you can actually have the designs, for example, so that you have a band stop region right here by defining a high pass filter which starts here, meaning the low pass, original low pass cutoff frequency would be somewhere here. Okay, so those are the tricks how to handle FIR filters. Next, how to make the IIR filters. In a moment, I'll go first and say